Welcome to G Fun Facts Online. Today we are diving into a discovery that sounds like it was ripped straight out of a science fiction novel, yet it is happening right now in a laboratory in Austria. We are talking about a state of matter that should logically exist. It is a material that is simultaneously a rigid crystal and a flowing liquid. It is called a supersolid, and for over 50 years it was considered the holy grail of quantum physics, a theoretical ghost that haunted the chalkboard but refused to show itself in the real world. But recently, that changed. A team of physicists at the University of Innsbruck has not only created this paradoxical material, but they have also reached inside it, stirred it up, and witnessed the formation of quantum tornadoes. This is a story about how we finally visualized the invisible, how we proved that matter can be both stone and river at the same time, and how a tiny cloud of atoms in a vacuum chamber is helping us decode the most extreme objects in the universe, neutron stars. So let's strip away the hype and get into the rigorous details of how this actually works. To understand why this recent breakthrough is such a massive deal, we first have to break down our intuition about how the universe works. In our day-to-day lives, matter is binary. It makes a choice. It is either a solid or it is a fluid. If you look at a solid, like a block of ice or a diamond, its defining characteristic is spatial order. The atoms are locked into a specific spot in a repeating geometric grid, known as a crystal lattice. If you push on it, it pushes back. It has rigidity. It has shear modulus. On the other hand, you have fluids. If you look at a liquid, the atoms are disordered and flow freely. But in the quantum world, there is a special kind of fluid called a superfluid. This isn't just water or oil. A superfluid, like liquid helium-4 cooled to near absolute zero, possesses something called phase coherence. It flows with absolutely zero viscosity. If you stir a cup of superfluid, it will spin forever because there is no friction to slow it down. For decades, physics told us these two states were mutually exclusive. You cannot have the rigid spatial order of a crystal and the perfect frictionless flow of a superfluid at the same time. It is a contradiction. But in 1957, and later refined in 1969 by Russian physicists Andreev and Lifshitz, theorists proposed a loophole. They suggested that in the bizarre world of quantum mechanics you could have a material that does both. They called it a supersolid. Imagine a crystal where the atoms are arranged in a grid, but they are also delocalized. This brings us to the concept that Francesca Ferlano, the pioneer behind the recent Innsbruck discovery, calls the Schrödinger's cat of materials. In a supersolid, the atoms are arranged in a density modulation that looks like a solid lattice. However, because these atoms are cooled to mere billionths of a degree above absolute zero, they behave like waves rather than particles. They share a single macroscopic wave function. This means that while there is a probability spike of finding an atom at each spot in the crystal grid, the atoms themselves are free to tunnel and flow between these spots without losing energy. The material holds its shape like a solid, but its constituent atoms flow through that shape like a superfluid. It is a mind-bending concept, and for 50 years it was just that, a concept. The scientific community spent decades hunting for this in solid helium-4. In 2004, there was a massive announcement from Penn State claiming they had found it. They saw a mass decoupling in a torsional oscillator, which is a fancy way of saying part of the solid wasn't spinning with the rest of the container. It looked like a supersolid. But, in a heartbreaking turn for those researchers, it turned out to be a mechanical artifact. The helium's elasticity had changed, not its state of matter. The helium supersolid was a dead end. This failure taught physicists a crucial lesson. Nature doesn't give up its secrets easily, and simply freezing a liquid wasn't the right path. To build a supersolid, you have to engineer it from a gas. This brings us to the University of Innsbruck and the dipolar revolution. The team, led by Ferlano, stopped looking at helium and turned to dysprosium and erbium. These are rare earth elements, and they have a superpower. They are highly magnetic. This is the key technical detail that changed everything. In most ultra-cold gas experiments, atoms interact like billiard balls. They only affect each other when they physically touch. This is called contact interaction. But dysprosium atoms act like tiny bar magnets. They possess dipolar interaction. This means they can feel each other over long distances. They can attract or repel without touching. By cooling a gas of dysprosium atoms to about 50 nanokelvin, the researchers created a tug-of-war between two forces. The short-range contact repulsion wants to keep the gas puffed out as a cloud. The long-range magnetic attraction wants to pull the atoms together into clumps. By perfectly tuning these forces, the gas spontaneously organizes itself. It forms high-density droplets arranged in a neat, crystalline grid. This gives you the solid part. But, and this is the magic ingredient, these droplets are not isolated. They are bathed in a low-density background of atoms that connects them all together. This background acts as the superfluid glue that allows flow between the solid islands. So the Innsbruck team had the crystal structure, and they had the coherence. They had created a supersolid state. But creation is not proof. They needed a smoking gun. How do you prove that a rigid crystal is actually flowing without friction? You can't just touch it. It is in a vacuum chamber colder than deep space. The definitive test for superfluidity is rotation. This brings us to the heart of the recent breakthrough, the observation of quantum tornadoes. To understand this, we have to look at how fluids rotate. If you spin a bucket of normal water, the water eventually spins with the bucket. It rotates as a rigid body. The water in the center moves slower than the water at the edges. But a superfluid breaks the rules of classical mechanics. If you spin a bucket of superfluid slowly, nothing happens. Because it has zero viscosity, the walls of the bucket slide right past the fluid. The fluid stays perfectly still while the container spins around it. It refuses to rotate. However, if you spin the bucket fast enough, the superfluid is forced to react. But it doesn't start spinning smoothly. It breaks the rotation into discrete, tiny packets of angular momentum. These packets are called quantized vortices. Think of them as mini tornadoes. They are tiny hollow tubes that pierce through the fluid. The fluid swirls around these holes at specific speeds dictated by Planck's constant. In the center of the vortex, the density is zero. It is a singularity. If the Innsbruck team could see these vortices inside their supersolid, it would be irrefutable proof that the material was a superfluid. But there was a problem. A supersolid is incredibly fragile. It is a delicate balance of opposing quantum forces. If you spin it too hard, the centrifugal force rips the droplets apart and destroys the crystal. If you spin it too gently, no vortices form. The team, including lead author Eva Cassotti and theorist Thomas Bland, had to develop a completely new technique called magnetostirring. Since the dysprosium atoms are magnetic, they didn't need a physical spoon. They used an external magnetic field to gently rotate the atoms. They didn't just spin the field, they wobbled it. They created a rotating potential that coaxed the supersolid into motion without shattering it. They cooled the atoms, navigated the phase transition to the supersolid state, and then applied this magnetic stir. Then, they snapped a picture using imaging techniques that reveal the density of the atoms. The results were breathtaking. In a standard superfluid, vortices look like random holes that eventually organize into a hexagonal pattern known as an Abrikosov lattice. But in the supersolid, the team saw something entirely new. They saw the distinct holes in the density, the cores of the quantized vortices. This was the first direct imaging of vortices in a supersolid. But crucially, these vortices were not floating freely. They were interacting with the solid structure. The solid droplets and the fluid vortices were locked in a complex dance. The vortices tended to settle in the low-density regions between the droplets, where the energy cost to drill a hole is lower. But their presence forced the crystal lattice to rotate along with them. The images showed the solid droplets swirling, and nested between them were the telltale dark spots of the quantum tornadoes. It was visual proof that the material was flowing through itself. The solid structure and the superfluid flow had synchronized. Now, why does this matter? Why should we care about spinning atoms in an Austrian lab? Because physics is universal. The behavior of the very small often mirrors the behavior of the very large. The most famous supersolid in nature isn't in a lab. It is inside a neutron star. Neutron stars are the collapsed cores of dead supergiant stars. They are incredibly dense. A teaspoon of neutron star material weighs 1 billion tons. They also spin wildly fast, acting as cosmic lighthouses known as pulsars. Astronomers observing these pulsars have noticed something strange. A pulsar is supposed to be a perfect clock, spinning with exact regularity. But occasionally, they glitch. They suddenly speed up before slowly relaxing back to their normal rhythm. For years, theorists have believed this is caused by superfluid vortices inside the star. The theory goes that the outer crust of a neutron star is a crystalline lattice of iron and other nuclei, a solid. Inside, there is a sea of neutrons acting as a superfluid. As the star spins, millions of quantum tornadoes form inside. These vortices can get pinned or stuck to the solid crust. When the stress becomes too high, they all unpin at once, transferring a massive kick of angular momentum to the crust, causing the star to speed up. That is the glitch. The Innsbruck experiment essentially built a scale model of a neutron star. The dysprosium droplets act like the neutron star's crust. The background gas acts like the neutron superfluid, and the magnetostirring mimics the star's rotation. The researchers observed the vortices moving through the lattice, getting pinned and influencing the rotation. They effectively created a glitch in a bottle. This discovery provides the first terrestrial, experimental backing for the vortex avalanche theory of pulsar glitches. It allows astrophysicists to test theories about the interiors of dead stars without leaving the planet. But the implications go even further, touching on the fundamental symmetries of the universe. In physics, we define phases of matter by the symmetries they break. A liquid has translational symmetry. If you move it to the left, it looks the same. A solid breaks translational symmetry. It has a specific pattern. A superfluid breaks gauge symmetry, which is related to the phase of the wave function. A supersolid is unique because it breaks both symmetries at the same time. The Innsbruck experiment showed that these two broken symmetries are not enemies. They talk to each other. The elastic waves of the solid and the flow of the superfluid interact, confirming that the superfluid fraction is robust even when the density is highly modulated into droplets. Looking forward, this opens the door to simulating even more exotic physics. One major area is room temperature superconductivity. Superfluids and superconductors are cousins. In a superconductor, electrons flow without resistance, just like atoms in a superfluid. The vortices in a superconductor determine how much magnetic field it can handle before it fails. By studying how vortices move through the crystal of a supersolid, scientists can gain insights into how magnetic flux lines move through high-temperature superconductors. If we can figure out how to pin these vortices better, we might be able to design materials that conduct electricity perfectly at room temperature, which would revolutionize energy grids and electronics. Furthermore, this system acts as a playground for 2D quantum hydrodynamics. It can be used to simulate turbulence, chaos, and even acoustic black holes. There is also the potential to simulate the nuclear pasta phase of neutron stars, where nuclei are stretched into shapes resembling spaghetti or lasagna deep within the star's crust. The dipolar supersolid, with its tunable droplet shapes, is the only system on Earth capable of mimicking this geometry. In conclusion, the image of a quantum tornado spinning silently inside a crystal is a powerful testament to the strangeness of our reality. It reminds us that the rigid boundaries we perceive, solid versus liquid, frozen versus flowing, are merely illusions of the classical world. At the quantum level, opposites can coexist. The work of Francesca Ferlino, Eva Cassotti, Thomas Bland, and their team has turned a 50-year-old mathematical curiosity into a tangible reality. They have stirred the unstirrable and watched the impossible swirl. As we gaze into these tiny, swirling vortices of dysprosium, we are not just looking at a clever lab trick. We are looking into the heart of neutron stars, into the future of superconductors, and into the deepest fundamental symmetries of nature itself. The supersolid is no longer a ghost. It is here, it is spinning, and it is spectacular. That wraps up this deep dive into the world of supersolids. Thanks for listening to G Fun Facts Online.